the Future of Tech Talks panel. So this is the second kind of lightning talk discussion slash panel that we've had or that we're having currently. And yeah, let's just get started. So our first speaker will be Holly Sun, who is currently a full stack engineer at Capital One. Holly graduated from the University of Michigan in 2019 and shortly after joined the TDP program as part of Capital One. She's currently working in the Chicago office as a full stack engineer and primarily works on features to improve the credit card application. Some of her various tech stacks are shown there, and it's JavaScript, React, Java Spring Boot, AWS, and I'm sure she can speak a bit more about that as well. So without any further ado, Holly, you could take it away.
All right, thank you so much, Rashad. Yeah, I'm Holly. I'm from Capital One, and so yes, I graduated in University of Michigan in 2019. I am part of the technology development program, which, from what it sounds like, most of you will either want be thinking about the internship program or the development program is for those of you who are graduating. I work on improving the credit card application process for Capital One. So that includes anywhere from like front-end UI work to dealing with some of our back-end systems, which are written in Java Spring Boot. And then a good amount of our services are hosted on AWS Cloud Services. So yeah, that's a little bit about me. And then Rashab, do you have further slides or should I just go directly into my presentation?
Sorry about that, I was muted. Yeah, you could go into your presentation. Let me know if your screen share works.
I will give it a shot. Let's see. Oh, let me get to. Give me one moment.
Sure.
All right, can you guys see my screen?
Yep, we can see your screen.
All right, fantastic. All right, yeah, so I'm Holly from Capital One, and to start with, I'm going to tell you a little bit more about the company. That is me. I'm a software engineer, as I have already said. So a little bit about who we are. We were founded in 1994. Our CEO is Richard Fairbank, and we have currently over 50,000 associates. On the top here, you'll also see the different locations where we have our tech offices. So Richmond, McLean, so that's the nice building that Rashad was talking about. Plano, Chicago, New York, San Francisco, and Boston. And here you'll see our different lines of businesses or LLBs. So we have card, which obviously the credit card aspect of the company, serving more than 87 million customers. We have the commercial bank, which does loan portfolios. We have small business, we have consumer bank, and of course we have auto finance. So in terms of the programs we do offer a variety of programs, not just technical programs. For our internships, we have, along with our technical internships, design, finance, human resources, and management internships as well. For our full-time program, we have the technology development program that I'm in right now, so I can speak more about that if you're curious. We also have the cyber rotation program, for those of you who are interested in cybersecurity. And something else I want to note, in case any of you are interested, the other program that I think is pretty cool here is the Capital One Developers Academy, or the CODA program, which is meant for people who did not graduate with a tech background but want to make the transition. So you'll be entered into like a 6-month boot camp and then transition into a TDP role afterwards. And then, of course, we have programs for graduate students as well. Next, I'm going to talk a little bit about our diversity, inclusion, and belonging initiative here at Capital One. So what we're really trying to do is create a culture of belonging where everyone can thrive and innovate, attract and develop talent from all backgrounds and experiences, and ensure our systems and programs promote fairness and equality. And that's something that we've been trying to do through a variety of ways. And one of those ways is through our business resource groups, which are very much like just your college campus student groups. So we have Ola out front for our LGBT plus associates. We have Empower Her. We have Origins for our Asians and Pacific Islander associates. And of course, we have Salute for our veterans as well. And so those are just sort of the different ways you can find these small subgroups within the Capital One community. And to go beyond that, we also have sort of these business resource groups or BRGs specifically for our tech associates as well. So here you can see a variety of different BRGs that are just specifically for our tech folks. And now I'm going to tell you a little bit more about those internships and full-time opportunities that I described earlier. So the TDP program, the Technology Development Program, is a 2-year program where software engineers get to strengthen their skill set through a diverse set of roles and experiences. And this is the program that I'm in right now. So if you have more questions about it, I can answer it more specifically later on as well. The core components of the program include rotation, learning, development, and networking. And I'll tell you a little bit more about what those mean. So for the rotation, you get 2 different assignments. So your first year, you'll be with one team, maybe learn a little bit of backend, or maybe deal with some infrastructure stuff. And then the next year, you'll be rotated onto a different team who can do something completely different, maybe front end, maybe mobile programming. So this gives you a really good chance to explore different technologies, learn from different leaders, learn from different management styles, grow your professional network by just being able to connect with different areas of the company. So this is a really cool way to sort of try different tech stacks and just get a wide breadth if you're interested. In terms of our internships, the technology internship program is a 10-week summer internship for students 1 to 2 months away from graduation. So for the role, you'll be collaborating, you'll get to collaborate on a diverse and passionate team of engineers. And then at the end, you have like this one big project that you've been working on for the past 10 weeks, and you get to present that project to your senior leadership. You get to learn from a variety of different technical skill base and competency, and also you'll get different leadership trainings throughout your program as well. Development, so you get a support structure of mentors and managers. So your manager will have maybe bi-monthly or bi-weekly or weekly meetings with you to discuss what kind of maybe tech stacks that you want to work with and sort of help you with your growth. Or you'll also be assigned, I believe, a TDP mentor who will help you with, who will sort of just guide you along the way, maybe sit with you at lunch, that sort of thing. We also have networking opportunities where there will be hackathons, there's fun social events, lots of things. And now a little bit about how to actually be interviewed for these programs. So our technical programs interviews consist of what we call a power day, which is just a giant day of different interviews. So all interviews this fall will be virtual, obviously. And there will be 3 different interviews, behavioral, technical, and case, not necessarily in that order. So most of you will be pretty familiar, I think, with behavioral and technical interviews. The case interview is more of an open-ended problem-solving question, and it is not necessarily technical in nature, but we're just trying to see how you can deal with a variety of problems. So like it says here, it'll deal with solving real world technology business problems, and it's related, but not necessarily like a straight up technical programming question. And it's just designed to see how you think, essentially. And if you wanted to apply for this program, so applications are open right now for full-time and internship opportunities. If you want to apply, please visit the campus.capitalone.com. Yeah, and I believe that's it. Now for the fun part, do you guys have any questions?
I actually have a question for you, Holly.
Yeah.
So I guess like on a day-to-day basis, like what sort of, I know you mentioned like the technologies that you work on, but how do you kind of apply those technologies into the actual work that you do for Capital One? And how does that affect your, I guess like end consumers?
I guess, I'm trying to think of a good way to answer your question. That's a good question. Okay, so in general, I would say the day-to-day technology that I work with right now is React and Java Spring Boot, and then specifically right now I'm working on some infrastructure changes. I would say the way that it affects the company. So if you get to work on the front end portions of the application, so we are maybe like button changes or maybe adding additional fields. So those are pretty straightforward. You'll be able to see it push to production. You can literally go to the website and apply for a credit card, and you can see your changes in production. In terms of sort of the backend changes and the infrastructure changes, I would say that those are a bit harder to see from the customer perspective. But once you understand how things work and flow through the different services, which is something that I enjoy, it's pretty cool.
Cool, thank you. I think we have a few more questions in the chat, so I could just read them out loud so everyone can hear. Steffi asks, what are some interesting projects that you've worked on in the TDP program?
Yeah, so some of the interesting, I'm just going to stop sharing. Let's see. So we have, one of the things that I've been working on is sort of getting a way to reach out to customers after they have been sort of pre-approved for a credit card. And it was interesting to me because it involved understanding a variety of how the credit card application works. And it also involved quite a different tech stack. So if you think about it from, let's say like a pre-approval form, you will have your email field, and from there it gets submitted to maybe some backend API that does the actual processing. And then maybe that backend API goes to some other data source, and you have to sort of find a way to pull all these data together so that we can actually give the customer, so that we can actually send a customer this like marketing email asking them, hey, do you want to apply for a credit card since we see that you've been pre-approved? So I truly enjoy challenges like that where I have to be able to see the flow through multiple systems. Hopefully that answers your question.
So Tejas asks, technically speaking, what sort of trends do you see emerging in the next couple of years?
Yeah, so I would say for Capital One specifically, a lot of our infrastructure has been moved to AWS Cloud. I think that's one of the biggest moves right now, is just to move a lot of capabilities to cloud. And what that does is it makes it so that we can really just spin up new infrastructure and new services really, really quickly.
That makes sense. So Samir asks, what drew you to work for Capital One?
What drew me to work at Capital One? So this is actually kind of an interesting question for me, because part of it, honestly, was the interview process, because I was at a point where I was a junior or senior in college and I started doing all these interviews. And one of the things I noticed was a, a lot of it is just you filling out a form and then someone maybe reaching out to you in email or sending you this link to go sign up for an interview. But prior to the interview, you really don't see people. So there's not like a name or a phone number you can really call. And with Capital One, when I was when someone picked up my resume, they called me and asked me if I wanted to come in an interview, explain to me what the sort of interview process was. And they actually had another TDP also call me, sort of walking me through how the interview is going to go as a prep. And I really, really like that aspect of the company.
Cool. Sounds good. Thank you so much, Holly.
Yeah, anytime.
So if we don't have any more questions, we'll move on to the next Future in Talk speaker. And the next speaker we have is Shivam Baruka from Facebook, and he's a production engineering at Facebook. And he works on the AI infrastructure team. Shivam received his master's and bachelor degree in computer engineering at UIUC. And during his time at UIUC, Shivam actually found interests in distributed systems, computer architecture, so some common topics for a lot of the classes that are in ECE and CS. And Shivam will share his experience in the industry and discuss the challenges of powering AI at Facebook.
Awesome. Thanks, Rishabh, for the introduction. Let me just share my screen. Can you guys see my screen?
Yep, I can see your screen share.
Awesome. Hey, everyone. Thanks for attending this talk. My name is Shivam Baruka, and I'm a production engineer at Facebook in the AI infrastructure team. Today, I'll mostly talk about how we scale machine learning at Facebook and in the industry itself. Before I get started on the talk, there is a Piazza link on top of the slide itself, and it has an event ID which you can use to sign up, and you'll get notification to other events we do so that you're aware of what's going on. So let me start by describing about my journey from UIUC to Facebook itself. So I started doing my bachelor's at UIUC in 2014. And during my undergrad, I did a couple of internships at companies like Delphix, which is like a small startup in the Bay Area. Then I moved on to doing an internship at Amazon and Google. After that, I extended my bachelor's to a 5-year master's program, which some of you might have heard of, which UIUC offers in the ECE department. And then once I graduated, I joined Facebook as a production engineer. So let me first talk about why production engineering instead of a more common role like software engineering itself. During my internship, what I realized was as a software engineer, I was working a lot on features and products which were fun to work, but not something which I wanted to do in the long term. I was always interested in debugging different pipelines, what's going wrong in the production. And I also enjoyed the OS class, the 391 class, which some of you might have taken in the EC department. So I wanted to do something at the systems level as well. So production engineering seemed like a good mix of both systems and SWE work. And this was one of the main reasons that I joined Facebook as a production engineer. So in this talk, I'll mostly talk about what machine learning is and what are the challenges we face while scaling machine learning at scale. So I'll first start off with the motivation itself, why machine learning, and then move on to describing the different machine learning pipelines and how we do machine learning in practice. Next, we'll talk about some of the challenges we face and how Facebook addresses them. And in the end, I'll go over my experience and why I chose this team in particular in amongst multiple teams which Facebook offers. So let's talk about machine learning. It's everywhere. As you might have known or seen that it's being used by multitudes of applications. The Netflix movie, you might have seen recommendation for Crown or Stranger Things. Those are powered by machine learning. Instagram tells you what pictures to discover in across the world. Those also come from some models which are trained to find out what you're interested in. Amazon recommends you the products which you keep on buying, and those are also coming from like your buying patterns, which are powered through machine learning. Similarly, Google Assistant understands your actions, what you're saying through natural language processing, which is like a subset of machine learning. Um, so, and if this doesn't convince you, let's look at some of the stats which are there. Netflix has said that they save over $1 billion just because of the recommendations they provide. And similarly, Amazon is able to like increase their sales by 35% by just like providing better recommendation for the products they should buy. So as you can see, like the impact of machine learning is quite huge. And it's not just limited to these tech companies. It's being used by other industries like manufacturing or pharma or whatever you name it. So now let's talk about like how we do machine learning and what it means to do machine learning. So roughly put, machine learning is basically training on a large amount of data and then providing recommendation based on that data. So suppose you have a production service like Netflix. It collects a lot of data about users, like what kind of movies are you watching, what age group are you in, and what are your preferences, basically. And then it uh, feeds this data into what we call a model. And the purpose of this model is basically to learn patterns. And this can be like, for a Netflix, taking the Netflix example again, this can be just if I click on an action movie and someone else is also interested in action movies, what movies are they watching? Are they from the same demographic? So it kind of tries to relate the users and what kind of movies you might be interested in. And then it serves users traffic based on that. So even though I might sign up today, it might look at just my demographics and find out what I might be interested in because of other people who are from the same demographics, what they are watching. So that is the main power of machine learning, making sure that it can connect different data points, find out patterns in those, and basically provide recommendation based on that. So what are the challenges in running machine learning? As you can imagine, like the number of products which use machine learning now, they're increasing rapidly. Companies are using more and more machine learning into their existing products. To give you an example, like nowadays, even in your G keyboard or Gmail, when you type, it recommends you like what you might want to type. That is also powered through machine learning. So these use cases are increasing rapidly. And with the use cases increasing, we are collecting more and more data about users. And once these data is collected, we want to provide like more granular recommendation to users. We want to look at more granular data. So that means like increasing the model itself. Like they look through more and more data points and find out more granular patterns which are there. And in the end, you have more user traffic coming on these platforms. So the entire pipeline is seeing an influx of changes and demands in terms of scale. So how do we address this challenge? So I'm going to talk about a few strategies which we employ at Facebook, but these are applicable outside the industry as well. Like Google is doing this, Apple is doing this, and many other companies which are there. And we have a lot of research groups working on this as well. So when scaling machine learning, you need to optimize both hardware and the software. Basically, you need to rethink the entire stack. The traditional distributed system algorithm or data processing algorithms, they need to be designed specific to machine learning itself. So you need to optimize how you process data, how you store the data itself, how you perform distributed training, which is like very different from just performing distributed computation algorithms you might learn in your distributed system class. Then you need to design special hardware for these as well. So like apart from CPUs, now we have GPUs and special hardwares which just run machine learning workloads. Apart from that, now we need to design ML pipelines which are scalable. As you can imagine, we have like thousands of researcher or industry companies doing machine learning. So we need to make it accessible for them. So that like everyone doesn't need to know and optimize the stack, but it's easy for them to just like take an existing stack and play around with it. And the way I see it is machine learning is a tool. It's not a discipline anymore. In the future, like right now computer engineers need to learn programming. That's a prerequisite. Machine learning is going to be a prerequisite and a tool which they employ at their day-to-day job. It's not going to be limited to special engineers who are like just doing machine learning as their core job. It's going to be like used everywhere. So my experience, and why does this interest me, and why should you be interested in this as well? You get to solve really hard problems. As I mentioned, like you're redesigning the entire stack. So that's basically challenging all the basic principles or all the basic algorithms you might have learned in your classes. So that involves solving like really hard problems and rethinking them from scratch and pushing the industry as well. Um, so one thing here is from my personal experience that when you join a company like Facebook, Google, or any of these big tech, you have like thousands of employees there and like multiple teams which you can join. How do you know that what you're working on is actually impactful outside the company itself? And since machine learning is so new and every industry and every company is trying to do it, it's the right field to actually increase your impact. So whatever work you do in this field is gonna just push the industry and like help you like make proper impact. And the application itself, like I mentioned, it's being used in manufacturing, pharma, supply chain. So the applications of what you do are like quite a bit. So that's why I think this is the right field to be in, and that was one of the main reasons I ended up joining AI infrastructure team at Facebook. I think that's all I have. I'm going to open it up for questions. You can ask me anything about like the classes you should take, the job at Facebook, machine learning. Thank you.
Actually, I have a question, Shivam.
Go ahead.
Yeah, so I don't know if you might have mentioned this at the beginning of your talk, but I guess you're a production engineer at Facebook, right? So obviously one of the most common roles is like software engineer for like, any of like these big tech companies. So can you kind of go over a bit and maybe let the audience know what the differences between your role and like the software engineering role is, and especially like at Facebook?
Yeah, for sure. I think production engineering is a quite unique role, which is there at Facebook. There are some similar roles at other companies like Google has site reliability engineer, but it's not exactly the same. So what production engineers do is they focus not just on writing features or products, but they focus more on like scaling the product. Like they focus on performance, they focus on efficiency of the product. They focus on how the product behaves in the production environment. Like, is it working reliably? Do you have like proper monitoring setup so that if a user faces an issue, you can go fix it immediately or with like immediate pace? And I would say like the time split of the day-to-day job is also different. Like a SWE would mostly spend like 80% of their time writing features and 20% maybe just doing some debugging. With these, that changes a lot. You are spending 50% of your time debugging and finding out like bottlenecks in your stack, and how you can make it more efficient. How you can save machines just by like changing few lines of code. So doing some performance engineering there, and then 50% is spent in like designing the product itself from the beginning, helping SWEs write the code and make sure the product is designed so that it can serve properly in production. So I would say that's a major difference between these two.
Yeah, that makes sense. I think Tejas had a question. Tejas asks, what are some of the most important classes that you took at UIUC? And do you have any recommendations on courses to take if someone is interested in software production engineering?
Yeah. With production engineering, we test a lot of the system skill. So anywhere from operating system, networking, storage, memory, all those stuff. So I would say one class which is very important, and it's one of my favorites at UIUC, is the EC 391. That's the operating system class. It's supposed to be the toughest class in the curriculum, but I would say if you actually pay some like time to it and express some interest, those concepts are like really interesting. And that's one of the most useful classes for if you want to prepare for a software production engineer role. Apart from that, like I would say classes on networking class, which is in the CS department. I forget the number, 438 or something, and distributed system class, which is also there in the CS department. Those are also very useful to learn all the basics for this.
Severe asks, why did you choose to work in AI at Facebook versus some other companies that may be leading AI applications in tech?
Yeah, so one of the main reasons for, actually, there are a couple of reasons here. Uh, One of them is like, I really like the production engineering role at Facebook. That was not there at Google. I had interned there in the past, and the SWE role, which I was doing there, that was not as cutting edge. And if you see, uh, Google is way ahead in AI in terms of like the industry. So joining Google doesn't make sense compared to like a company where it's still like being developed. You're rethinking all these technologies. So that also made sense at Facebook. Apart from that, there is a very cool program at Facebook called Bootcamp. So at other companies, when you interview, you directly join a team. They assign you, okay, this is the team you're going to join once you start full time. At Facebook, what they do is they put you in a pool of all new engineers who have joined. And for 2 months, you just sit with multiple teams and find out which team you're interested in. So you get to like sit with AI, you get to sit with like core kernel teams or whatever team you want to, and decide what you're interested in. So that kind of gives you the flexibility on what you might want to do in your job itself. So that was, I think, one of the main reasons to join Facebook.
Sure. Steffi asked, you mentioned that machine learning is expanding into many fields like pharma. So what's an application of machine learning in pharma?
Yeah, so one of the biggest application there is right now a popular research area in pharma is genome sequencing, which is basically understanding the DNA of a human and making medicines more specific. Like right now, when we design a medicine, these are going to be very generic. They are mostly applicable to most people who are using it. But like in future, we want to make it more specific to a particular person. Like based on some genome sequencing, we can do based on their DNA itself. And machine learning kind of helps us do the sequencing algorithm itself, like make sure it finds patterns between different DNA molecules and recommend you what medicine might be proper for this one. And this is like kind of in futuristic. There are some cool applications which have been implemented already as well in medicine. One of them, which was announced recently by I think Facebook or Google, is the X-ray process was improved using machine learning because of how because of the amount of data we have collected in the past, like X-ray data we have collected in the past. Doctors were able to find out more patterns and strategies to actually deal with different kind of diseases. So there are a lot of applications. It's all about like how you interpret data, I would say. If any field has a lot of data, machine learning helps in finding those patterns. You don't want a human person sitting there and sniffing through all the data to find like, okay, this might be something which might be related and useful to look into.
Yep, makes sense. So does anyone else have any last questions? So Kelly asks, why did you decide to pursue the MEng program at UIUC as compared to other graduate programs? And what advice do you have for someone pursuing graduate school but is unsure about a master's in engineering or a master's with a research thesis in MS?
Yeah, that's a really good question. So I did face this issue when I was in my third year or fourth year. I think there were multiple reasons in choosing MEng versus MS. One of them was based on my internships. I realized that the gain you get from a master's degree is quite limited compared to like if you end up doing a PhD, then it's a different ball game. Then you go for a research position at different companies, or you go for like a academic position in university itself. With masters, it was in terms of when you enter the industry, it's seen as like as equal as the bachelor itself, because computer engineering is more about like the projects you do and things you work on. It's not a lot about the degree itself. Like a popular theme in Silicon Valley is to drop out and do a startup. So nobody's technically looking for a degree there. The reason I decided to do an MEng was I needed some time to find like a proper grasp on one of the concepts I was interested in, like distributed system. So I wanted to deep dive into it. And I felt like a MEng program, which can be done in an extra year, was a proper fit rather than an MS program, which takes like 2 years and gives me kind of the same knowledge. Because my aim was not to do a thesis, but more to just take more classes, grad level classes, and understand these concepts in detail. And I feel like that really helped to get an edge when I did join Facebook. Like inside AI infrastructure as well, like we have a lot of engineers, and once you have like a deeper understanding of these distributed algorithms, you get to like work on the research side as well. Like I frequently collaborate with AI researcher at Facebook and the SWE team just to make sure, so since I have an understanding of like some of the core algorithms as well. So that has really helped in my experience.
Well, yeah, good answer. I think a lot of people have that question in terms of whether to do the Master's in Engineering or MS program. So
Yeah.
thank you so much, Siobhan. And if Kelly says thank you as well. And if there are no more questions, we can move on to the next speaker.
Awesome.
So,
Thanks, Rishad.
Yep. I'll share my screen again. Cool. So our next speaker is Julie from NVIDIA. And Julie's team focuses on several aspects of deep learning systems, including performance and large-scale deep learning deployments for hyperscale and cloud services. I actually forgot to mention this, but she's actually the director for deep learning system software at NVIDIA. She joined in 2015 after about 15 years in academia as an expert in ML for computational structural biology. She obtained her PhD from, I don't know how to say that, but I think the University of Paris, studying geometric and statistical models for modeling protein complexes. And after doing a postdoc at Stanford with Professor Michael Levitt, who was a Nobel Prize winner in chemistry for 2013, she joined another company, she joined INRIA, which is the French National Institute for CS. And while she was a senior research scientist at INRIA, the adjunct associate professor of computer science at École Polytechnique and visiting research scientist at SLAC, her work focused on computational models for structural bioinformatics, specifically storing functions for macromolecule docking using ML and statistical potentials for molecular simulations. So without any further ado, Julie, I will give you the stage.
Hello, thanks, Rishabh. Sorry that you had to go through my whole pedigree in academics. I can relate to the previous question. Can you guys hear me very well? Is that okay?
Yeah, we can hear you.
Cool. So yes, I can relate to the previous question. Whatever you choose something you like. You can have a twisted path, as you're gonna see, and end up doing something you like at any point in time. So let me share my screen if you allow me to do that. And I'm trying to find the right. Okay, can you guys see my screen right now?
Yep, I can see your screen.
Perfect. So today, I'm going to present to you about something that you guys might be familiar with, but I'm going to present you my view of it. I'm going to present you supercomputers for AI. So you've seen AI, you've seen infrastructure, you've seen production. Here I'm going to present you the Formula One of AI and how you build it, and how that at the end a lot of AI relies on a bunch of cables. So I hope that's going to be interesting to you. So I work for NVIDIA, as Rishabh said, and I work for NVIDIA, but I don't game. So I have a beautiful gaming laptop that I'm not using for gaming at all. As was described, I did my career mostly in academia. I joined NVIDIA 6 years ago. And I did that because I have an interest both in GPU computing and AI, and also because I like playing with toys. So today, most of you have heard about NVIDIA. Most of you, know what we do. The idea here is to show you the projects of a couple teams, and specifically what we built, to show you the different type of resources and the diversity of people we need to build a big project. So this is a classical slide that you guys might have seen. So just for the little story, when I did my PhD, was there, like the GPUs were, you know, very fancy, new shiny objects. And what's very important is here, you can see single-threaded performance and multi-threaded performance. So what's very important here is it's not only a hardware story, but it's also a software story. The way we do software has changed dramatically, right? And so whatever you guys decide to do, this is very interesting to see how it's going to, we need to be flexible and how we need to be able to understand the whole stack in the story. People don't often know that, but NVIDIA has more software engineers than hardware engineers. You know, a lot of people see us as a hardware company. No, we're a lot of software people. And I consider myself software person, even if we're a technically systems person. We're going to cover that. So what do I call AI, deep learning, and the new computing model? So basically what I'm going to show you here is a focus on training, which is taking billions of trillions of a lot of operations, gigantic data sets, putting them into some kind of training strategy to be able to run inference somewhere in a car, on the edge, on the security camera, this kind of thing. And that is what is usually called inference. Quick drawback, quick comeback to when I was a student. I show you that curve, you know, it was, oh, prep your data, go and have a coffee. When I started my PhD, actually a neural net was actually too big and too complex to be computed. So get another coffee, wait, get another coffee. And I like this because I stole that slide from Colleen. It's like switch to decaf. Yes, because that was a very cumbersome process. And AI is one of the topics where the quality of your infrastructure is going to give you the capacity to iterate. So again, a little bit of a story. I joined NVIDIA 6 years ago. So that was here, right? That's where we were. You know, that's how the time we need to train ResNet 50. So if you guys remember, ResNet 50 is the network that helped win the image recognition competition in the past, right? And at the time, to be able to do that, you needed 25 days on a single GPU. And through a lot of engineering and algorithm and improvements, we went to 20 hours, you know, on a single machine, to 8 hours, to 70 minutes, to 6 minutes on a cluster, to 1.33 minutes. And right now we're under a minute. And that's on the compute side. On the model side, the models are getting bigger and bigger and more complex. So that's an example of the number of parameters in the neural nets over time. And again, AlexNet, so that was, you know, before all those things, the ResNet that I've shown you before are here. This is logarithmic scale, right? Here I got GPT-2, I haven't plotted GPT-3, but right now we're right there. And so interestingly, the complexity keeps on increasing. And the more you want to do, the more you have to compute. So it's directly linked to the amount of infrastructure you got. Doesn't mean we can't be smart. No, it doesn't. That means if we get everything to be better, we have a shot of being able to train better networks. So just to give you an order of magnitude, for the number of words, for example, you need to train a language model is around 2.5 billion. For label data, like, you know, images that a car brings every day. So a car brings like 1 terabyte of data for every 8 hours of driving, kind of. So if you have a pretty beefy laptop right now in front of you, a car will bring as much data as your hard drive can contain every day. That's a lot to manage. And the reason I'm showing that to you is because at NVIDIA, we have all those people working on the supercomputers we have, right? We have people that do AI development and performance, where every night they checked whether their code's getting better. So that's an example of a GitLab CI. That's an example of a Kibana dashboard, if you guys are familiar with it. That's an example of a language modeling competition. We have people coming with the car and doing analysis of the data every day. And we do have a lot of software. And so we have to QA everything, making sure it works for everybody. So to be able to do that, we need supercomputers. This is an example of a supercomputer we built last year called Celine. It's a DGX A100 SuperPod. So that's a funny name for a computer that can fit in a data center, which can be deployed very, very fast. It takes a couple months to put on the ground. And that has a very interesting design. So basically, it's using cold and containment design, because at that scale, what you care about, it's basically the same thing you care about on your laptop. It's making sure it doesn't eat too much and making sure it doesn't crash because it's too hot. So power and thermals are two of the things that are very important here in a data center. So behind the scenes, what does it mean? Are we just like putting a bunch of computers together? Do we care? No, we're not putting a bunch of computers together. And a supercomputer is made of a very fast storage system. So I was talking about the file system earlier. This computer has 4 petabytes of data as a scratch system that is used every day. You have a bunch of cables doing super fast connections between the different machines that are represented in green. And you have those nodes that are basically supercomputers by themselves. Why do you care? You do care because a lot of those technologies require capacities and require you to be familiar with a lot of different things. So here we're going to have a pretty big topology on what we call a fabric. A lot of it has to do with graph theory, right? It's a fat tree. It's a fat tree with some redundancy here. You know, those graph 101 that with those weird exercise at the beginning, they're very useful in practice. So finding paths here is something that is very used in routing. Here I got something that is very cryptic, SHA-2 support for offload. So if some of you know, in parallel computing, we do a lot of collective operations like reduction, scatter, gather. If you've already used those words, right now you do that in software and you do that on the GPU or you do that on the CPU. But actually there's a capacity to do that in the actual networking switch. And when you have to combine as a software engineer, this capability on the switch, on the GPU, on the CPU, and at a very large scale, that could be a very interesting computer science problem. So, you know, it's just, that's easy. Now it's a big one. And then we design one and we make sure you can buy one, you can buy two, you can buy three, you can buy four. But expanding is harder than it seems, because I said it's a tree, it's a bunch of cables. So you have to design it right day one to make sure we can expand without having to redo everything. So at the base, what there is in it, and when we built that supercomputer, we also announced a new architecture, which we call the Ampere architecture that you see it. So those are the GPUs that are in this machine. Each compute node in this machine, I had 8 of those A180 gig GPUs. So here, there's a bunch of things here that are very cryptic, but are very, very important. That is the interconnect between the GPUs, how they talk to each other. This is the bandwidth of the memory of the GPU. And so the faster, the better, right? And there are some interesting things here, like the tensor core. And what that means is that's an operation. So those are the different software things the GPU, the architecture supports. And that's an example of what the TF2 tensor core thing means. A lot of things believe it's just, yeah, a marketing thing. Actually, no, it's a real operation. And if you've been to computer science classes and you learn to use FP16 versus FP32 precision and what the range and so on and so forth, when you start training very, very large networks, the capacity that you could have to do such operation in one go on some representation can actually be very, very important. In particular, when you care about the precision, right? So that's a quick example. I'll have a link for you later. What that means too is that with the same training, for example, in deep learning, or the same piece of software, if you can leverage those operations that are done in one clock in a GPU, can go much faster without having to worry about it very much in terms of code. Okay, so this is the machine that is contained in the cluster. So the cluster we have 560 of those machines. So I'm going to try to make it a little bit faster. I'm not sure you guys can get this sound. Whoops, my bad. I'm sorry. So the reason I like this video is because we can see what's inside of the machine. And basically, I like how we can see how different it is from a laptop or a workstation while being very, very similar. So we need to wait for the machine to fall from the sky. That's not how they come to the data center, just so that we're clear. But here is what's inside. So this machine is 6U, which is approximately that big. Those are the 8 GPUs. This is the chip with the memory on. The big thing you're gonna see on it is actually the heat sink, which is used to cool off each GPU. So they're connected together using an onboard fabric, which is called NVLink. So here are the NV switch, which are used to make the GPU talk to each other. Those need to be cooled off too. Remember, I mentioned you about thermals. Those are the cards that are used to make each machine communicate with each other. We have 10 of them in each machine. And that explains to you why the machine is so big. It's made of 3 stories. And here in front, behind the bezel, you have a bunch of fans. Basically, why is that interesting? So if you're like me and you like very, big toys, that's super fun. There's a lot of stuff to touch when they allow you to open it. But why do we care? We do care because it's not only GPUs. It's this big, big, big machine. And in particular, you also have to have it, the analogy I use is if you buy the engine of a Ferrari and you put it in a Honda, you're kind of wasting your time, right? And here, basically, you have to have everything balanced to make sure it's right. So if some of you know the equivalent of this, if some of you are gamers and you have a big Ryzen CPU that you're just trying to get your hands on to redo your gaming machine, those are the data center equivalent, and they are very, very big. They are 128 cores. So to program those CPUs, it's actually a little bit challenging, especially as we're using hyper-threading. So you see 256 core total. And they're attached to 8 GPUs using PCIe. So even balancing the workload right to make sure that, everybody's talking to the right people requires pretty serious programming attention. We also have to work with pretty recent OSs, in particular Linux kernel. I heard the previous speaker say, yeah, you might want to go in, in the OS class. Yeah, those classes are hard, but they are very fun and they're useful later. Trust me. So yes, we run a bleeding edge Linux kernel to be able to support that CPUs. And there's a lot of it. We look at the system side of it. We also have a lot of internal storage because we do a lot of caching for performance. So here you can see how, people working with us, and I have some performance engineering in my teams, you can see how much fun they have. It's not only debugging, it's also tuning, so that can be fun. Okay, quick on the fabric, those machines are connected together with giant fabrics, a lot of cables that are faster than your Ethernet cables. Here we're using InfiniBand. It's 200 gigabit, what we call HDR. And this is a pretty big fabric. So we have 850 switches that account for more than 10,000 cables. And it's a plain fat tree network. So here is all fat. It's the core level. Here's the spine level. And this is the leaf level. So that picture is ugly, but it's a good engineering picture where it shows you the challenges of routing a signal and doing collective on such a network. Storage. So it's just to show you what it looks in real life, right? So this is a 52U rack. That's a real Celine picture. So I'm 5'4", like to reach the top, I have to raise my hand, right? And this is my hard drive. And this is 1 petabyte of storage. So yeah, I mentioned you cooling and so on, but even the weight of it. And this is the connection that my 1 petabyte of storage needs to reach all my 560 nodes. So it's, and this is relatively small in terms of density. We managed to make it very compact, but that's the kind of size it takes. Trying to speed up a little bit, working together. I like very much saying, should you do engineering, should you do CS? At the end, just do what you like, because to be able to build something like that, you need people having skills everywhere. I've been trying to mention performance engineers. I can mention data center operators. I can mention people doing automation, people doing software. I mean, you know, there's a job for everybody. Quickly to make you laugh, I'm a big cable fan. There's a Reddit channel that is very famous when people do cables. You know, I show you the front of the networking rack. That's the back. It's just a close up, right? And the computer is so big that we have cables that are more than 50 meters. So if you see what is an Olympic pool, that's actually the length of a cable. And that's how you bundle such a cable. That means that's how you put them together as you lay them out to make sure they don't get entangled and so on. And so here is the ladder in the back. And this is a real picture. I didn't cheat on it. So that's a 50-meter cable bundle. It goes all the way through, comes back over there. Setting up such a machine requires a little bit of organization. So even the challenges, you know, one would never believe that one of the challenges is making sure it's cabled right and everything works fine, but maximum performance is there at that cost. Quick mention on software. I'm not going to spend a lot of time on it. You guys might be aware of CUDA, and I've been doing GPU computing. So just a couple of links for some of the latest CUDA release, what they do that you might not be aware of, that I put here in the slide deck for your attention. We also have a deep learning SDK where we provide containers for different frameworks like PyTorch, TensorFlow, and so on. And what I like very much is they work everywhere. So the same container that runs on my laptop to be doing my little experiment to, I don't know, recognize pictures or denoise the background is actually, so that container is the same that would run on Selene. And actually we test them on Selene at scale so that they can do multi-node. So this is also the link to the ID on NGSA containers. We have a libNVIDIA container, so we're capable of supporting Docker, any Singularity, or we even have our own container runtime called the nroot. So again, going back to the OS class, you know, this kind of thing. It's actually pretty interesting if you want to have a look at. Okay, scale to multiple nodes. It's the same thing with containers that can be a little bit challenging. So if you want to have a look at what it looks like in practice, I have links for you at the end. And why do we do that? So a lot of you might be familiar with GitLab, GitHub, and all the systems to be able to validate. That supercomputer we use for our own purposes. What that means is every time we release a container, we have customers that's going to take that container, run it on Azure, run it on Amazon, running at other cloud service providers, or running on their laptop. It has to be validated. And so our all automation and so on is able to automatically kick off a job on the supercomputer. So that's very funny because we can also use that as a constraint. So if you guys are used to push PR to GitHub, if you push a PR and request a merge to master on one of our deep learning container internally, it has to pass at scale validation. So that means you have to be ready to debug on a supercomputer, which can require a little bit of getting used to. Moving on, we watch everything that supercomputer does, from its power consumption to its temperature to the fabric it has. And in green, that's the occupation of the supercomputer. So you can see it's very much used. Those things, as soon as they work, are very, very useful. So, and they're expensive, so they can't stay, you know, doing nothing. Especially we're in California, so you know the power grid in California sometimes has challenges. So this machine is also very power efficient, which means we can cut some of its power while keeping its performance for a while. Same thing, we monitor a lot of things behind the scenes, the GPU power, the thermals, the temperature, etc. I'm going to pass. I'll have some links for you. Couple links. This one I like very much. I'm going to click on it real quick. It shows a little story, and it shows that because of the pandemic, we have to adapt. And so we have a little guy in a data center that goes and checks cable for us when we can't and are worried about something. So we named it Trip, because at the beginning there was so much mess everywhere in a data center that we would worry it would make us trip everywhere. But I gave you the link to that blog, and that blog has details on how we did things. Let me return, and I cannot return. How do I change that? Here we go. Sorry about that. Last but not least, if you're interested in knowing more, because I didn't spend time on the different type of position, please have a look at the survey here and see your interest. I try to keep in my 20 minutes, not to take too much time, but there are a lot of different opportunities over there that I invite you to go and have a look at. Thank you for your attention. I'll take questions.
Thank you, Julie. I actually had a question just to get us started, I guess. Yeah, so my question was, so considering that you're like such like a professional or like in deep learning, what do you see as like one of the more impending like bottlenecks for deep learning? So obviously we have like thermals that you mentioned within a supercomputer, and there's a huge thing that I think a lot of people don't realize is like data, just training data. So what sort of, I guess, impending bottlenecks do you see that maybe NVIDIA or other, leading companies in the world have not taken care of that might need to be the next big jump to make that jump for training deep learning networks?
It's a very good question. It has so many different angles. It's going to be hard for me to to answer. So the first angle is, I mean, you guys so one problem we tried to solve with Selene, because we made it generic so that we can cut it in little chunks and anybody can have a chunk. And one problem that we tried to solve at NVIDIA, which for me is a real plus, is as a researcher, I want to test my ID. There's nothing more frustrating than having an ID and not being able to test it because you don't have the hardware or you don't have the software to do so, right? You want to do a demo, you want to test an ID, you don't want to spend 3 weeks setting things up. Mm-hmm. It's like, I remember my PhD or my PI saying, yeah, just look at it. I was like, oh my God, that's all I need to do. So the first challenge that is getting solved is getting started. I feel like we made a lot of progress, making sure everybody can run real quickly and get started. Then having access to that infrastructure. So the cloud is great and is helping, being able to have also affordable infrastructure at the university level and infrastructure where everybody can run the same thing. It really helps for me when I can prototype on my laptop, before the pandemic, being in the train, but prototype in front of my TV on my sofa and just push that on the supercomputer and not have to worry that I have to recompile everything. Sounds lame, but as you said, I'm seasoned. That means I'm not young. It used to be that compiling was really painful. So this kind of thing. Now the challenge is going to be systems are getting more complex. And to be able to test an ID or test something, the overall complexity makes the hyperparameter search or the tweaking and tuning very expensive. And while algorithms are helping and we want to run everywhere, including on the edge or in our cars and so on. Being able to prototype quickly and iterate while being very stable requires a lot of, knowledge, a lot of experience and so on. The amount of math classes that one didn't imagine having to take just to be able to follow machine learning 101, right? We would all like to push the button and make it work, but no, we have to go through that whole linear algebra thing. And it's very useful, and getting an intuition of it comes with experience. So that's required a lot of work. So I would say, working on it getting experience for me is the most challenging, because that takes time, and none of us wants to spend the time. Right? We want to play right away.
That makes sense. I think Tejas had a question. He said you mentioned that you started off in computational biology. Do you mind talking a bit about your journey from computational biology to deep learning systems software?
No, I don't mind. It's a great question. So as I said, I graduated in chemistry because I've never been very strategic about my career. I've always went with the people that were nice to me and that I enjoy at the time. So at the time it was chemistry, and then I was like, oh yeah, they're doing biology. That seems nice. It smells a little less bad. Okay, let's go and try and see what they say. And so you can see on my LinkedIn, it's no secret. I was in a university in the early 2000s, and it was the beginning of the T1 line. So we had the giant internet cable that nobody had, right? So what I did is, like everybody, I spent my evenings not really doing my own work, but more playing with friends. At the time, I was playing a lot. Yeah, I'm not very good at Quake. Don't mention it. Let's not go there. But yes, that was before Unreal. I remember that. And so basically, I wanted my life to combine both computer science, what I like, and biology. And I met somebody say I wanted to do a PhD. I like geometry, and you meet somebody that knows somebody else. And I did machine learning because I was teaching programming at the university as a TA. And the friend I was teaching with was actually doing his PhD on, genetic algorithms, right? And so I worked on, and so now it's famous. At the time, it was not, on protein RNA interactions. So, for example, the spike of a protein is going to attach to another protein, right? So it's very funny because right now everybody knows those words. At the time, nobody, it was not as public knowledge. And I was doing machine learning to try to predict those interactions. So basically, our virus would attach to a cell, or our virus would capture RNAs and work on RNA dynamics. And what happened is, to be able to do machine learning on that, I had to do a lot of computations. I had to train myself at becoming a somewhat decent computer scientist. So, and I restarted computer science. I was in master's, so that was an interesting one. And I had to be willing to do the extra work to go from the theory to make it work in practice. And that means going on supercomputers and so on. So I made a lot of mistakes. I've wasted a lot of compute hours, right? But at some point in my life, I saw, that amount of biological data that I didn't know what to do with. I realized that I knew machine learning, that since I trained myself and being surrounded by people who helped, I knew how to do that. And even at NVIDIA, I didn't start as an engineer. I wanted to see the world. So I started as a solution architect, where I was basically helping customers port their codes to GPU and do AI on the GPU. Just because I wanted to see the world, I wanted to see how people did it. And I remember very vividly the people who helped me when I had to do it. And I wanted to do that. And one thing leads to another. Then you need a little cluster. How about you build it, and so on? Are you sure you don't want to do engineering? Yeah, and eventually I did engineering. If you look at what I did at NVIDIA, I had several positions, which relates to the question that was asked earlier. At NVIDIA, we have programs where we can rotate between other teams, especially if you're Neural College grad. You can come in and apply something, you get hired, but it's a big company and there's always an opportunity for you. It's actually the opposite problem. Sometimes you have to say no to people because you don't have the time to help them or work with them. And that was very difficult for me initially. Did I answer the question? Thank you. Okay, so yes.
Does anyone else have any questions? Seems like no one has any questions at the moment. I'm just still trying to process everything you said.
I'm sorry.
No, you're good. You're good. It's just like a lot of, I think, especially like deep learning, there's like so many terms and, sorts of like terminologies that's like thrown around. I think it takes some time, even if you've like maybe taken a class in the past, like fully understand what the implications of, one thing or another might be.
And my messaging was maybe it's not a big deal. Maybe you can have the time. The terms that we use right now, you're going to use them for 1 year, for 2 years, and then yeah, it's going to change, or some other area is going to get fashionable. And I've overwhelmed you guys, just like, oh yeah, here you go, just look at all this. And it's not to show off or anything. It's just to say that if you start being honest at what you're trying to do and you're honestly interested, people will trust you and they will give you bigger and bigger toys. And you'll keep on playing. At least that's how I did it. And at the end of the day, whatever you guys decide, it does matter, right? But if you do that with passion and you don't, you try to do it right each time, people will trust you to the next thing.
I think Severa had a question. She asks, with such a varied and uncharted career, what doubts and challenges did you face as you moved from different positions and technologies?
That's a very good question. I have a strong imposter syndrome, like everybody. I know when you see me like that, you say, oh, she looks very confident. No, I'm like everybody. When I try something for the first time, I was like, why are they trusting me with that? I come from a country that, is not always as open as the US are, with a woman working in computer science and engineering, right? So I've been in cases, it's getting better, but I've been in cases where I enter the room. I go to the data center in Eels, for example, which is against the security policy. Don't tell anybody. It's not safe, but I do that. People look at me sometimes as if I have the wrong room. One learns to overcome that. For my imposter syndrome, I was like, you know what? We're all imposters. My better half has a saying, which is, oh yeah, in blind people's kingdom, one-eyed peoples are kings. What that means to me, the way I interpret that is, make sure you do your best. Make sure you try to do it right. Make sure that when you don't know, you say you don't know. Call a friend. It's like that. So what's the name in English? Who wants to win billions or something? It's just like you have several opportunities to call a friend to help you. And that's okay. And for me, failure, being afraid to fail is a big problem, especially when you're early in your career. Failure is good. Failure means learning, right? I'm going to have to pardon my French. It was like, if you knew how many oh shit moments we had when we built that thing, I was like, oh, it doesn't fit. Crap, we thought it would. Right? It sounds lame, but being ready to try to pivot and fix anything will help you. Knowing when to fix and when to accept failure is also okay too. If you pick a class and you suck at it and you don't like it, even if it's fashionable, don't do that. You're just going to make yourself miserable. And I made myself miserable several times. and that's basically it, is to find something you like, you're going to have to experiment. That means you're going to fail. And that's okay. See that as a learning experience. I'm sorry, I sound like an old person here, or I sound like a parent or like an uncle or something. And I know it's lame, but it really helped me.
No, I think that's good advice. So Tatus had another question. He asks, you mentioned a lot about powerful supercomputers. So with the exponential growth of internet devices generating lots of data, do you see supercomputers needing to depend more on edge devices than they currently do?
It is a very good question. So it's complicated, and I'm having a little bit of trouble answering that question. So supercomputers and edge devices, are they really that different eventually? When in the 90s there was this fashion of like agent computing, and if you read the Michael Christian book, you have like agents and so on. At the end of the day, those are machines working together, right? One of the challenges when you work on the edge and you have a supercomputer is making sure you handle access control and security and who does what when properly. And that is a real challenge. At the end of the day, you have a lot of data flow. Controlling which data flows where, according to which policy, right? If you work on medical data, you have specific constraints. If you work on private data, depending on which country you work in and which data you deal with from which country, you might have to have different access control. I think eventually it's going to be more integrated. It's going to be less edge to supercomputer. It's the in-between is going to be more of a flow, but I'm still challenged to see what the mid ground is going to be. And I wouldn't make a prediction, right? It's like the stock. It's something that we can see it's coming. I'm still, a lot of it's going to be software defined. That's for sure. What's going to happen in practice? I don't know. I wouldn't make a bet.
Thank you. Severe asks another question. She said, as you mentioned, failures serve as learning experiences and help people grow. So what are some failures that you have encountered that have helped evolve your work ethic? And what are some other lessons that you have learned from those failures?
Okay, so I'm going to try with a non-technical one. I'm a French native. In French, we say, I broke my computer. It doesn't mean I broke my computer. It means my computer broke. But in French, you cannot say my computer broke. So when I came here talking with new college grad and so on, I would come and provide feedback saying, you broke it, or it's bad, it's not working, fix it. Okay. And I didn't realize that that was very mean. That I didn't realize that I was actually attacking people like that. I meant, hey, it's broken. Can you help fixing it? Right? But I said, hey, you broke it, fix it, which is different. So that's something I learned the hard way. And that's one of my biggest failures, which is I offended people without wanting to. And you know, we hear a lot right now about diversity and about how we involve everybody. I made mistakes without willing it. And so you know, it was mentioned work ethic. I think now I pay a lot of attention to that. And it's helping me very much. It's helping me very much because a lot of us come from different cultures, different countries, different background. We have different opinions, different views. And it took me, I'm a hardcore engineer. I come from academia, so I would tell it to you like it is, right? It's broken, just fix it. And it's actually difficult when you work as a team. You can achieve more, but being able to include everybody and provide adequate feedback for everybody to grow is very, very hard. And that's now what I learned from that is that if you do it right and try to apply to yourself and to everybody the same level of excellence you would like to see by respecting people achieve great things. I have a guy in my team, if he sees that, he's going to recognize himself. But 2 years ago, he knew nothing about file system. Now he's the lead engineer on a parallel file system, the one you've seen with 4 petabytes of data. And he debugs it every day when there's a problem and so on, right? Just, you know, getting the best of people sometimes, you just need to ask them and showing them what they do wrong. Yeah, maybe do it nicely. But it's, you know, it's always, for me, it's something that as an engineer or that in academia, I didn't learn. And that's helping me very much right now. A team asking for help, that is something, or being able to say no. If you don't know how to do it, and to say, I don't know, I'll try, but don't say you're going to do it. Overcommitting is the worst thing you can do, right? You put everybody in trouble. So set expectations, try to be nice, try to be honest, and eventually it's going to go. Be careful or you provide feedback. Don't do the same mistake I made. That was, it took me too long to figure it out. And it still happens. I was like, what the heck is going on? And then on the technical aspects real quick, whatever you plan, something's going to go wrong. So, you know, I show you those cables. We measured, we did prepare and so on. The hole is always too small, just because there's always something. You always run out of Velcro, right? Tuesday, we had to make an emergency call. The power cable for what we needed to do was too short. You know, at the end of the day, you don't want to have a super big machine or something you care very much about to be waiting or to be not working very well because you forgot about a 1 cent chip or a $2 cable. So plan ahead, plan for plan B, and plan for plan C. That's my second lesson, and all the way up to Z, because something's going to go wrong.
Makes sense. Actually, I have a question for you, Julie. I have another question for you. So I think last year marked your, I think, 5-year anniversary at NVIDIA, right?
Yeah.
So what do you, I guess, see as like your next venture in life? Obviously, maybe you're staying at NVIDIA for the rest of your career, but is there anything else that maybe you want to accomplish?
Oh, that's a good thing. I'm at a point in my career that, so I was very anxious about the future and so on for a long time, because as I have a past that is, I'm going to say, a little bit unconventional, right? I was very anxious I would not find a shoe that would fit my foot, right? And honestly, I don't know. And what I'm going to tell you is it doesn't matter. I'm going to stay with the people that keep me happy and keep me having fun, right? I didn't start at NVIDIA with this lean budget. I started at NVIDIA. I was like, here's your laptop, figuring out this customer has a problem. Like, okay, sure, I'm going to look at it. And then we built a small cluster and it worked okay. And we built a bigger one. And then we built this one, right? And so I said I like toys. So I like to experiment with a technology that we don't know whether it will work or not, right? So my job at NVIDIA right now is advanced development. The project that I presented you is over, right? So the next project is going to be something new again. What I tell people is at NVIDIA, I made myself a reputation. I like breaking things when they're not supposed to break. For example, I'm very unlucky. I touch a microwave, you can be sure it's going to be broken. I even found a bug in the firmware of my washing machine. I have a gift. I love breaking things, but if I break things for NVIDIA, then when you buy an NVIDIA product, it's not going to break, right? And so I like pushing everything to the corner of how it should work, to make sure we could try explore something else. If you had told me 10 years ago that I would have a supercomputer, I would have laughed at you. I was like, yeah, sure. So I honestly don't know. I'll keep on playing, right? And the day it's going to be more fun to play with something else, maybe I'll do. But right now, I have nothing to prove. I'm good where I'm at. I have a fantastic team. We have, Animal Crossing island parties because it's the pandemic, so we can't go to the bar anymore. And we're a bunch of people having fun every day building toys. So what else can I ask for?
Yeah, I think that's a great answer. And I think honestly, that's probably what everyone is looking for by the, like after a certain point in their career when, they just want to like kind of stop work, like feeling like it's work and, actually just like have fun with what they do every day. So it seems like you reached that point, which is
and
awesome.
Be careful, guys. That's one of my interview questions. What gets you going in the morning? And you can't fake that one. No, more seriously, it doesn't mean that I feel like I've arrived anywhere. It's just I've never arrived anywhere, and I'm never going to be at the end of what I have to explore with. I'm the kind of person that might have a trouble retire. Some of those. Sorry.
Good problem. No. Does anyone else have any questions? I think this might be the longest Q&A session we've had, Julie. So
I'm sorry. I know.
No, I mean, that's a good thing. That means that might be the most interesting lightning talk we've had. I think Steffi asks, you've had an eventful career, so how do you keep growing your knowledge to work on new projects?
I'm curious. So I don't know whether I do that intentionally or not. I'm curious and I'm incapable to sit in a formal class. I shouldn't say that to you guys, but I have a hard time paying attention to a class all the way through because I'm very curious. So my mind races here and there and so on. So the way I do it is I always make sure that whatever I'm interested in, I push it to a certain level of achievement I'm going to take something that is completely non-technical to make you laugh. It was 10 years ago, I decided I would learn crochet. And I learned on YouTube. And then I made toys for my cat. It's lame. It's completely, but I felt good doing it. I don't do it anymore. But I can show you. More seriously, machine learning, when it got famous, I went and I did the Coursera class like everybody, because I was advising them to the people I were working with and my students. So I wanted to know whether I was still, good doing that. And yeah, I did them. I did so at a very certain age, being a full-blown academic. I went and I registered to Coursera class. No shame, right? We can always learn. There is no shame to learn. So learn, get the certificate. It could be anything. It could be in your job. It could be, I learned scuba diving very, very late also in my life. I can go on like that. I'm very curious, but make sure you get it to the point that you get certified or you get a milestone or you can attest of it. Because it's good for you. You feel like you've achieved something. But it's also good to show to the world that you're capable of pushing something through all the way to the point where it's interesting. And I'm not going to say that it was always fun. I graduated in chemistry. That means I have a lot of quantum mechanics classes. I'm still remembering them vividly, and I feel for that teacher. I was a pain. But down the road, eventually it worked. I hope I answered that question. It's very hard for me to explain how to grow your knowledge when I'm not a great learner.
Let's see. I don't think we have any more questions, but if anyone else has any questions, feel free to put it in the chat. Okay, cool. Seems like we don't have any more questions. Thank you so much, Julie. That was very insightful. I personally had a great time just hearing about just a lot of different things about your learning experience throughout your life and your career. And yeah, just thank you so much.
Thank you so much, everybody. Bye, guys.
Bye.
We have another event coming up at 6 o'clock. We have the CPO of Relativity, Chris Brown, giving a spotlight talk. And then following directly after that, we